All right, this is page 4 of our notes for today. We have already taken a look at the derivative numerically, graphically, and algebraically. So now we're just going to do a few review type problems and pulling it all together. But first I want to introduce a new notation. Given that y equals f of x is our function, we can write the derivative as f prime of x and as dy dx. And let me tell you what dy dx comes from. It's actually written right down below. This is, by the way, it's called Leibniz notation, German mathematician from a few hundred years ago. The letter D stands for a small difference in, and it actually comes from delta, which means change. So basically, if you think about slope, so y2 minus y1 over x2 minus x1. Back in Algebra 1, your teacher might have said this is really delta y over delta x. And we have these little triangles as the Greek symbol for delta. Well, now make that change so small. Remember the graphic where we had a curve and we wanted to find the derivative at this point, so we found another point so microscopically close that they were effectively on top of each other. So the change in those points, we take, instead of using the Greek delta, we are going to use the lowercase d for a tiny change in. So literally dy dx is the same thing as slope delta y over delta x, but it's incrementally or infinitesimally small changes in both y and x. So this truly is just difference in y values divided by difference in x values. And we say that this is the derivative of y with respect to x. Y is the dependent variable, x is the independent variable. And we will use Leibniz notation for several things in this class where standard f prime of x notation gets very cumbersome, and dy dx really helps you do the calculus. So you have to get used to it, and you'll see it 50-50 along with f prime notation. So now we're saying find a formula for dy dx algebraically if y equals x squared minus x. So they're asking us for basically the slope of the tangent line for any point on the function. Not just like on the prior page we did where a equals 3. Now we're doing for any x value. So we're going to use the definition of the derivative, the limit as h goes to 0, and we want f of x plus h. So everywhere where we had an x, we'll plug in x plus h. This component, these two terms, are f of x plus h, minus f of x. So that's just your standard function that you started with that you're subtracting, all over h. And now we're going to do a whole lot of foiling. So let's FOIL the first term to get x squared plus 2xh plus h squared. Let's distribute this negative sign to have minus x minus h, and then let's distribute this negative sign to get minus x squared plus x. That is all over h. Now we need to start canceling. X squared minus x squared goes away. Negative x plus x goes away. Now do you see that all three of the remaining terms in the numerator have an h in them, here, here, and here, and this term has an h. So what we can do is factor out an h in the numerator to get 2x plus h minus 1, and of course we're all divided by h. Let's not drop the concept of the limit. We're taking the limit as h goes to 0, and we want to cancel these h's. Now we can do direct substitution because all we have is the expression 2x plus h minus 1. When we sub in h equals 0, we get 2x minus 1. This is dy dx, otherwise known as f prime of x. This is the derivative function that represents the slope of this graph at any point x on the graph. So if I wanted to find the slope where x equals 5, I would just plug in 5 and I would find out that the slope of the tangent line where x equals 5 is 9. A disadvantage of Leibniz notation is that it's really awkward sometimes to specify the x value where you're taking the derivative. So we'd much rather write f prime of 2 rather than dy dx. This vertical line means such that. It is the math term for such that. So this phrase actually says take the derivative dy dx such that x equals 2. Much more concise just to use f prime of 2. So let's do a little bit of a review problem. We have s equals f of t, which is a distance in meters of a body from a fixed point in time, from a fixed point as a function of time in seconds. So that means that the units are going to be meters per second for the derivative. So let's talk about A. It says describe in the real world what this means, ds dt such that time equals 2. It says that at time equals 2 seconds, this is the instantaneous rate of change. Instantaneous rate of change in meters per second of a body from a fixed point. Now let's talk about the important parts of this. I gave the exact time, I gave the units, I gave what's happening. It's a body from a fixed point, and I said it's the instantaneous rate of change. We said that the units here are in meters per second. That's going to be our answer to B. What is the common term for ds dt? Well, all you physics people will know that this term is going to be velocity. So then the question is, what is the real world meaning of f prime of 2 equals 10? Use units. So in a sentence, I would write, at time equals 2 seconds, the fixed body, not the fixed body, we'll just say the body's distance from a fixed point is increasing because, of course, the velocity is positive. Velocity positive means distance is increasing at 10 meters per second. And that's it.